In this video, we're going to introduce the concept of the recursive definition of a sequence. In the previous video, we defined arithmetic sequences as sequences like this one, where to get from one number to the next in the sequence, you add the same amount. 6 plus 4 is 10, 10 plus 4 is 14, etc. And we saw that we can define arithmetic sequences using general terms like this. This is a formula where if we want to get, say, the 100th term, term 100 would be equal to 4 times 100 plus 2, or 402. We also saw how to develop this general term in the first place, given the sequence. Now, though, we're going to introduce the concept of a recursive definition, and a recursive definition defines each term in the sequence by relating it to the previous term. Here, the second term is the first term plus 4. The third term is the second term plus 4. The fourth term is the third term plus 4. The 100th term would be the 99th term plus 4. So any term is equal to the previous term in the sequence plus 4. And the algebraic way of writing that is t sub n is equal to t sub n minus 1 plus 4. This is any term, this is the previous term in the sequence. Now that's not quite enough to define the sequence, because you can imagine that this could define a sequence like this one, 0, 4, 8, etc. It could also define 1, 5, 9, etc. They all follow this rule. So we have to pin the sequence down by specifying what the first term is. And the first term in this case is 6. So we have to write both this part here, any term is equal to the previous term plus 4, and we need to write the first term. Now, this part of the rule applies to the first term, and this part of the rule applies to all the other terms. To specify that, we write that it applies when n is a natural number, that's a counting number, and when n is greater than 1. So if n is equal to 1, we apply this rule. This gives us the first term. Otherwise, we're applying this one. So that's the sort of more formal mathematical definition of this sequence using a recursive definition. 2 parts, basically. What's the first term, and what's the rule that applies for all the terms after that? So let's do an example. Give a recursive definition for this sequence. It's easiest to start off by writing down the first term, because that's part of our definition. The first term is 4, and we can also see that the common difference, we're subtracting 5 each time. The common difference is negative 5. So any term is equal to the term before it minus 5, and we specify that this applies for natural numbers for n. So we write that, and this part of the rule applies when n is greater than 1. If n is equal to 1, we're back to here. So that's the full recursive definition for this sequence. Here's another type of question. What are the first 4 terms in this sequence? We're given the first term is 2, and for all the terms after that, we apply this rule. Any term is 2 times the term before it plus n plus 1. Let's walk through the first 4 terms. So term 1 is just given to us, it's 2. Term 2, we've plugged 2 in here, so we get 2 times term 2 minus 1 plus 2 goes in there, plus 1. So that's equal to 2 times term 1 plus 3. Now we need to look up term 1 from before. Term 1 is 2, so that's equal to 2 times 2 plus 3, which is equal to 7. So term 2 in the sequence is equal to 7. For term 3 is going to be equal to 2 times term, we plug 3 in here, we get term 3 minus 1 plus 3 plus 1. Therefore, term 3 is equal to 2 times term 2 plus 4. We look up term 2, that was 7, so we get 2 times 7 plus 4 is equal to 14 plus 4 is 18. And you can see that the tedious thing about the recursive definition is that if we wanted to work out term 1000, for example, we need to work out term 999. So it's not very helpful for large number terms in the sequence. For term 4, we get 2 times term, we know how this works now, term 3 plus 4 plus 1. Term 3 is 18, so we get 2 times 18 plus 5 is equal to 36 plus 5 is equal to 41. So this sequence goes 2, 7, 18, 41, and then continues. So that's an introduction to the recursive definition of a sequence.